Hello and welcome back to my channel. In this lecture, we will be covering dimension reduction. Now, what is dimension reduction? It is a crucial technique for simplifying data and improving performance model by identifying and removing redundant or correlated variables. We can achieve greater insight, reduce computational complexity, and enhance model accuracy. Introduction to multicollinearity. First, definition. What is multicollinearity? It occurs when independent variables in a regression model are highly correlated, making it difficult to isolate the individual effect of each variable. Second, what are the consequences? It can lead to unstable and unreliable regression coefficients, making it challenging to interpret the results accurately. Third, identification. Several methods can be employed to identify multicollinearity, including correlation matrices, variance inflation factors, VIFs, and condition indices. Detecting multicollinearity in R. Correlation matrix, the COR function in R calculates the correlation matrix revealing the strength of linear relationship between variables. Variance inflation factor, the VIF function forms the car package, provides VIF values indicating how much the variance of a coefficient is inflated due to multicollinearity. Now, detecting multicollinearity in Python. Correlation matrix, the CORR method in pandas calculate the correlation matrix highlighting pairs of variables with high correlation. Variance inflation factor, the variance inflation factor function from the stats models package provides VIF values helping to identify variables with high multicollinearity. Understanding principal components analysis. First, data transformation. PCA transforms a set of correlated variables into a smaller set of uncorrelated variables called principal components. Second, dimensionality reduction. The principal components capture the maximum variance of the original data, effectively reducing the dimensionality without significantly information loss. Now, third, implementing PCA in R. First, PRCOM function. PRCOM function in R performs PCA calculating principal components and their corresponding eigenvalues and eigenvectors. Second, what are eigenvalues? Eigenvalues represent the variance explained by each principal component, indicating the importance of each component. Eigenvectors represent the direction of each principal component in the original variable space, showing the linear combination of variable defining each component. Now moving to the next slide, interpreting PCA results in R. Screen plot. A screen plot visually displays the eigenvalues of each principal component, showing the variance explained by each component. Cumulative variance. The cumulative variance experienced by the selected principal components indicates the percentage of total variance captured by the reduced dimension. Component loading. Component loading represents the correlation between the original variable and the principal component, providing insights into the meaning and contribution of each variable to reduce dimension. Now implementing PCA in Python. The PCA class is scikit-learn provides an efficient implement of PCA, allowing you to easily calculate principal components and analyze the result. Explained variance ratio. The explained variance ratio attribute provides the proportion of variance explained by each principal component, helping to identify the most informative components. Component loading. The components attribute contains the loading, showing the linear combinations of original variable defining each principal component. Interpreting PCA results in Python. First, scatter plot. Visualizing the transformed data points into the reduced space, helps to understand the underlying pattern and relationship within the data. Component loading bar chart. A bar chart illustrating the loadings of each original variable on the principal component reveals the significant variables contributing to the reduced dimensions. Applying PCA for dimension reduction. First, model building. PCA can be reduced the complexity of models by reducing the number of input variables, improving training time and potentially boosting accuracy. Second, data visualization. By reducing the dimensionality, we can more effectively visualize and analyze the data, leading to better insight and understanding of patterns. Feature extraction. PCA can use to extract meaningful features from complex dataset, providing a more concise representation of the data that can be used for downstream analysis. Now, this is the end of the slide. Thanks for watching. If you liked the video, please subscribe to my channel.